morning, everyone. My name is Piotr Banasiński, and I am Senior Data Scientist at deepsense.ai. I specialize in computer vision problems, and today I have for you the amazing presentation, great presentation about amazing topic, about the topic of data generation for real-world problems with diffusion models. And the effect of this presentation is the result of internal project at deepsense.ai. And in deepsense.ai, we, in the whole team, we work on the problems of data generation using diffusion models for real projects. And this should be emphasized that this is especially for real world applications. And in the team, we have a few members. Beside me, there is also Natalia Czerep, Tomasz Biegus, our newest member, Marianna Parzych, and also our past member, Paweł Olszowiec. Let's go to agenda. Today, I have a few things to discuss with you. And the first, I want to discuss the abilities of the modern diffusion models. I do not focus on the architecture and details of diffusion models. I assume that you have already some knowledge about the diffusion models. Then because of that, I go to the main topic of this presentation. This means that data generation. And in the second point, I describe some problems which we have with the data generation using off-the-shelf models. Why we couldn't use this data generated by the pre-trained model diffusion models in real-world projects. Then I go to our main assumption of these projects, and this assumption we can summarize with the sentence that we should use the light and fast methods because the diffusion models are heavy models, very large architectures, and they are not the best one for the real projects, but I will describe it in the proper moment. And after this introduction, I go to the main part of the presentation where I describe the main methods for the expanding data sets with data generated with diffusion models. And I cover topics like the data augmentation, domain adaptation, and also labeled data generation. And we finish with a short summary. Okay, let's go to the abilities of the diffusion models, of the modern diffusion models. If we check the papers of methods like stable diffusion, Dalle-E or image gen, Imagen, we can see that the results are absolutely amazing. These methods can generate realistic images with completely unrealistic, if we want, with unrealistic situations, with different styles and with a lot of different concepts. But if we want to use such methods, there is some problems. But let's start with the question why we should use these diffusion models to generate data. In the computer vision field, we need a lot of data to train the models. And this is the problem of most of the real-world projects, the missing data, the lack of data. And because of that, if we have the possibility to generate this data, I think that we should use this opportunity. Because the collecting of the real world data is time-consuming and costly. We need to collect the images, photos, or videos. Then we need to label this data. And if we have such problem like semantic segmentation, then this labeling process could be a very they take a lot of our effort. What is more, the generating of synthetic data have a few advantages. For example, we can increase variety of our data set very easily, because if we have method for the generation of data, then if we see that our data set is too small or the variety of the data set is not enough, then we can easily increase the number of data points. We can also omit some legal and privacy issues, because the data which we used for the training, they are not real data. We can also create some corner cases, or for example, create the better balance between some classes in our data set. And all of this we can do with diffusion models if we find the proper method for the data generation with these models. I said that we need to find the proper method, because there is some problems with the off-the-shelf models. For example, when we check the results of these diffusion models, off-the-shelf diffusion models, and we compare these images or data with the real examples from the real data set, from the real problems which we found in real projects, then we see similar situation like in the commercial of fast foods. When in the commercial we have a very nice looking, tasty hamburger, but in real we have a untasty sandwich. And if we generate data with stable diffusion, for example, hamburger, we have a very similar situation. We generate all of the generated hamburgers will looks like from the commercial. They looks very tasty. The contrast of the photo is very nice, and we have also the image is also nice cropped. And in the real projects, we have probably on the other situation where the images will be not cropped correctly, or we have wrong light conditions, or our objects looks completely in a completely other way than in the data generated by the stable diffusion. This is the one problem, but there is also the other problems with this synthetic data generated by diffusion models. One of them, this is that this models works well for the well-known concepts, like, for example, peoples, animals, buildings, cars, and some other common objects. But if you want to generate synthetic data with some unusual types of objects, then there is a large problem, because our images are not have good enough quality for the training. And for example, such a field where we couldn't generate the data with the off-the-shelf diffusion models, this is the medical data, because there in the training data set of the diffusion models, we probably don't have such type of data. Other problem with the data generated by diffusion models, this is the style of these images. For example, if we generate trash on the road with diffusion models, we get something like the image here, where we have one more time, we have a very nice lighting conditions, and also this image has style like the stock photography. But in the real projects, we have a different, very often we have different situation, because we work with the data which are taken with the mobile phones, or some other other devices which are not professional devices. Or for example, we work with the images or videos from the CCTV cameras. And because of that, there is this crucial difference between the data generated by diffusion models and the data which we meet in the real projects. And the last large problem with this data generated with diffusion models, this is the lack of accurate details. There is a well-known problem with the number of the fingers on hand, but also some objects in the background of the generated images are just a blobs, blurry blobs, and because of that, such images are not good enough for a task like image segmentation, where every pixel is important. Then we probably need to retrain these diffusion models to our task. But there is a second problem, because when we check how these these popular models like Dalle-E, Imagen, or Stable Diffusion was trained, we see that the training takes hundreds or even thousands of GPU days, and the data sets used to train this model have extremely large. They have millions or even billions of examples. And also the computational power used to train these models are very huge. Because of that, in our project, we focus on the methods which do not require such a huge computational power and vast data sets. It is important because if we have the real projects which have time, money, and access to this huge computing power, they probably in this project we also have space for the data generation because we have a large budget. We have also the time for the data collection. But there is a lot of small projects where the AI can improve the results where we have the limited resources and limited budgets. And especially for these projects, the data generation is important. And because of that, we create this general assumption of our project, which can be summarized that we focus only on the solutions that do not require the huge computing power and vast data sets. Okay, after this introduction, let's go to the methods for the expanding dataset, for the data generation for our projects. We focus on the stable diffusion method because the code of this method is open and we can use it in our projects. Also, there is a great repository diffusers which used the stable diffusion models and can be easily modified. And because of that, all of the results which I will show you on the next slides, this is the results which are based on this stable diffusion. But let's start with the different types of expanding data for our projects. For example, we can use the diffusion models as a data augmentation tool. This means that we do not generate new data points, we just modify the existing one. For example, if we have the image of track, then we generate the variance of this image, which with some small differences. The other types of the methods, this is a domain adaptation. The method where we have two domains, the source domain, source data set, and some target data set. We have a lot of, for example, we have a lot of source data, and we want to create a model which will be works for the target domain. And because of that, we can convert the source images in order to be similar to the target domain. And this this group of methods, let's call the domain adaptation. And the third group, this is a labeled data generation. This means that we in this group we create completely new data points, completely new images, but also completely new labels. Because if we want to use the data in our real project, then we don't need only an image. We also need the labels. As I said, the labeling of images, videos, or other type of data is very time consuming. And because of that, we want to create this data in order to use in the projects without any additional effort. Okay, then let's go to the first group, to the data augmentation. And we can use a few different techniques for them. For example, there is a method, image to image technique, where we generate the variant of the original image, adding only a very soft noise to our sample, to our input in image. And because of that, we at the end we have the image which is quite slightly different than the original one, but the composition, the structure of the image, the location of the objects is almost the same like in the input image. We can also use some dedicated methods for the data augmentation, and there is a paper, Data Augmentation with Diffusion models, and you can check this paper. The authors propose some method for dedicated for the data augmentation. But there is also the third method, which is my favorite one. This is the instruct to pix method, in which we can modify the original image using some instruction like make the photo, make the weather on the photo snowy, for example, or make the photo much more sunny or foggy. And this method is very, very nice because it works with the off-the-shelf method. We do not require any retraining or fine-tuning process because even if we put the images from our real data sets, they also works very, very well. You have some sample on the slide, and you can see that we can create the variants of the cityscape image, the image from the cityscape dataset, using only the prompt. And these methods didn't see before this cityscapes domain. This is the images which are generated just on the off-the-shelf model. Let's go to the domain adaptation, and here we can also try to use the image-to-image technique, which I described before. But there is the problem with this method, because if we add to the to very, very soft noise, then this image change very slightly, and almost the difference will be not visible. But if we add more noise, then some artifacts or non-existing objects appears on our generated images. For example, if we want to adapt the GTA 5 image to the cityscapes dataset, we have results like on the bottom of this slide. As you can see, if we add very soft noise, the image almost don't change. But if we add more and more this noise to the during the diffusion process, then we see that some not existing objects appears on the image, and if we add this noise, full noise, almost full noise, then the image will be completely different that the original one. And because of that, this method is not the best one for the real projects. But in our project at the deepsense.ai, we try to modify this method to get the better results. And we try the following concept. We use this image-to-image technique, but and we add very soft noise to the images, but we repeat this procedure a few times, several times, for example 10 times. And after that, with every adding noise, denoising image, and repeating this this process, the image change very slightly, but After several repetitions, we have an image in which we see some details which we see that this image was converted from into the direction of this our target domain. And here you have one example from our results where we have the image from the GTF5 dataset, synthetic dataset, and we try to convert this image to the cityscapes domain. And as you can see, the details and also the general characteristic of the image change in the change in correctly with our expectation. For example, if when the cars here are much more European, because the cityscapes is the data set containing images from the Germany cities. Also, the trees change the form. Also, the track looks in different way. Okay, and because of that, if you want to convert the domains with the diffusion models, we recommend to use such techniques, not the original image-to-image technique, but this technique with these additional repetitions. Okay, but now let's go to the data generation. At the beginning of this presentation, I told you that the retraining of or fine-tuning of the diffusion models is a very hard task because they need a lot of data and a lot of time and so on. But in fact, there are some methods for the easy and quite fast fine-tuning of diffusion models. For example, Dreambooth, low-rank adaptation method, textual inversion. All of these methods are described on our blog, on page of deepsense.ai page. And you can find the very nice blog post which describe how it works. Then if you are interested about that, I recommend to check this. And on the right side of this slide, we have a diagram which shows one of these methods from our the low rank adaptation. This graphic, this figure comes from this blog post. And I focus on this low rank adaptation, LoRa method, because we find that they is a very universal, useful for data generation with diffusion models. And also, what is more, the fine-tuning with this method is very fast, and also we don't need to require a lot of data. All tens or hundreds of images is enough to fine-tune our diffusion model to stable diffusion to our task. Okay, and we check how this LoRa fine-tuning works with the different concepts. And we group this concept into three groups. The first group, this is the well-known concepts, and here we use the data which probably have a lot of examples in the original training data set of stable diffusion. And here we have an example with the urban scenes. And as you can see, after the fine-tuning, we can reproduce the images from the original data. These data are very similar to the source data set, to our training data set. A similar situation we have for the second group, which we called poorly known concepts. This means that we probably have some examples of such images in original training dataset of stable diffusion, but we probably have only a very limited number of these such images. But as you can see, also for satellite images, the LoRa can generate the good quality images, which looks like the real ones. But in the case of the not known concepts, this method is not works the best. Because as you can see, maybe this generated images looks very similar to this on the top one. But if we check the details, we see that there some of the elements of these images repeat in the different places, or let's generally say that there is some differences which are difference between the source data and this data generated by our fine-tuned model. Then we can summarize that for these well-known and poorly known concepts, the methods like LoRa works well. Okay, but then we have only the image. Yeah, we using this fine-tuned model with LoRa. We can only generate the image. We don't have the labels, and because of that, in our projects we developed a method in which we generate not only the image using the stable diffusion model, but also the labels. And we use here some idea to add additional part which we called segmentator, which is a quite light decoder which produce not image but just mask, just a segmentation mask. This means that it will produce our labels for the image. And we in our method we train not only this segmentator, which is quite light because we use the hidden states of the original decoder from the stable diffusion. All of them other parts of the model were frozen, and we check that these methods works for some simple cases like pets, for example, pets in not usual conditions, like on the left side of the slide. But these methods, this segmentator also can produce image and segmentation mask for much more complicated cases, like in the case of the cityscapes. These images are generated with the stable diffusion, trained with fine-tuned with LoRa, and here we have the segmentation mask, which we generate with our segmentator. And in this way, we can produce the data for our project with semantic segmentation. There is also some methods where we can produce or generate image using labels, using some additional conditions. For example, bounding boxes or semantic segmentation masks, or even some edges or key points, for example. And there is a method like in painting stable diffusion, control net, or Gligen, in which we can create the images with structure or location of the objects controlled by us. All of these methods works in different way. For example, in painting, we use the latent space where we have information not only about the noise, about the noised image, but we have also about information about the background and also about the mask of the objects. In the control net, we have a large part encoder, large part which is encoder and process this additional condition. And in the model of Gligen, we have some additional layers, gated self-attention layers, which process this additional condition and also the latent space. And in this way, we can produce the image based on this additional conditioning. And as you can see, these three methods works similarly. The effect is very similar, but the architecture is completely different. And if we want to retrain all these methods like ControlNet, Gligen, or in painting, we see that we need to have one more time a lot of data, large computational power, and time, because all of these methods are quite heavy. But we find the great way how we can omit this problem. And one more time, the LoRa is the answer for the problem. We can train LoRa weights using the original text-to-image model. This means that we can use the typical stable diffusion model where we generate images using text and add to this such a model LoRa weights and train these LoRa weights, and then we can convert this, transfer these weights to other methods like Gligen, like ControlNet, or in painting. And the LoRa, because LoRa works on the cross attention layer, they fit to these other methods, even if they are not trained on this specific architecture. And when we check the results, we see that this method works very, very well. In the top row, we have the images generated with off-the-shelf models like in painting, ControlNet, and Gligen. And after this solution, which I described just before, when we train the LoRa using text-to-image stable diffusion and then transfer these weights to the in painting or ControlNet on Gligen, we see that we can reproduce the images which are almost fit to our target domain. We see that when we put the car using the in-painting method, the car not fit to this image. But if we use these LoRa weights, we see that we have results much more much better. The same situation in the ControlNet. If we use the ControlNet, which generate the images using the segmentation masks, we see that they create the image, but this is the completely different style than the cityscapes. But after adding these LoRa weights, we can reproduce the cityscapes images. We can generate this cityscapes images using the semantic segmentation masks. And also in the Gligen, in which we can use the bounding boxes. When we use the off-the-shelf Gligen model and generate the image with the dog and with the apple, we have the images which looks like on this top row. But if we want to generate dog and image with the dog and the apple in the style of the cityscapes, we can use these LoRa weights together with the Gligen model, and in this way we can very easily generate data in expected style. Okay, and this is all for today. Then let's sum up all of this presentation. Modern diffusion models are very powerful tools, and they have amazing results. But if we have to use them to generate data for real-world projects, we see a lot of problems. And retraining of this model, this is not the solution, because we need to have a lot of data. We need to have a lot of time and computational power to do that. But as I show you in this presentation, we can use a group of different methods to generate data with the diffusion models for our real projects, real-world projects, using the assumption that these methods should be fast and require not fast data sets. And the last information, if you are still interested about the diffusion models, you can check our blog on our page, where we have several blog posts which describe the diffusion model, but also the data generation with diffusion models. Okay, and this is all for today. Thank you for attention, and goodbye.